This is the exam 4 review, chapter 4, exam 4 review. Problem number 1. Approximate the number using a calculator. So you are going to have to do this on either your graphing or your scientific calculator. And on your graphing or scientific calculator, you should have an e to the x button. Now, whether it's above the natural log, which it most likely is, it's a key above your natural log button, so you might have to use second natural log to get to the e to the x. But you're going to raise that to the negative 0.05 power and hit enter. And when I do this on my calculator, you can see that they're using the squiggly equal. That means you're going to approximate it. And they tell you to round it to 3 decimal places. And when I did this on my calculator, I get 0.951. Problem 2, use transformations of the graph of f of x equals e to the x to graph the given function. Be sure to give the equation of the asymptote. Use the graph to determine the function's domain and range. All right, so what are we doing here? We got a couple of things going on. First of all, we're adding 4 to the functions, so that is a vertical shift. And it's a vertical shift of 4. The other thing we're doing is we're multiplying our input x by 3. So that is going to be a horizontal shrink. Remember, when you multiply x by a number larger than 1, that's a horizontal shrink. So that 3 is going to make a horizontal shrink. Now, when you graph this, you're basically just graphing the exponential and then shifting it 4 units up. So it looks something like this. Let's see if I can draw it, something like that. All right, and it does have a horizontal asymptote. And the original exponential function has a horizontal asymptote, that is the x-axis, or y equals 0. But when you shift it up 4 units, the horizontal asymptote also gets shifted up. So it gets shifted up to y equals 4. And when you graph this in MyMathLab, be sure that you graph the horizontal asymptote as a dashed line at y equals 4. So the asymptote is y equals 4. And you do have to type in the y equals. You can't just type in the 4. If you type in just 4 and hit submit, it's incorrect, and I will not count it correct. All right, what's the domain? Well, the domain of every exponential function in existence is the set of all real numbers. So from negative infinity to positive infinity. And what's the range? Well, the range of the standard exponential function is from 0 to infinity, but when you moved it up 4 units, you moved the range up 4 units also. So instead of being the set of positive numbers from 0 to infinity, it's going to be from 4 to infinity because you move the entire graph up 4 units. And you notice that we use parentheses on that 4 because this function can never equal 4. There's no value that I can input 4x and get e to the 3 times that equals 0. There is no value. So it's never going to be equal to 4. So we're going to use a parenthesis there. All right, problem 3. Suppose you have $10,000 to invest. Which of these 2 rates would yield the larger amount in 4 years? 7% compounded daily, or 6.88% compounded continuously. So you're going to have to use the 2 compound interest formulas. The first formula is for a discrete number of compounding periods. Discrete means you can count them. So compounded daily, you can count the number of compounding periods in a year. You can count that. Compounding continuously, you can't count that. So you're going to have to use the continuous compounding formula. So the one for continuous compounding, for this part right here, is A equals P times E to the RT. So we're going to plug in the various values we have for P, R, and T. So compounding daily, or the discrete compounding formula, is A equals P times 1 plus R over N to the NT. So those are the two formulas that we're going to use. All right, so what are we going to input into these two formulas? Well, the amount that you invest, the principal, that's P. So 10,000 is P. R is the interest rate, but it's the interest rate written as a decimal. So R is 7%. We're going to write that as a decimal, and remember, to take a percentage and write it as a decimal, you divide by 100. So that's going to be 0.07. All right, and then they tell me how long this is going to compound. 4 years. So T is equal to 4 years. All right, so we're going to make those substitutions into our two formulas, and then we're going to take our calculator out and let our calculator do the calculation for us. So we have 10,000 times E to the 0.07 times 4. That's our first formula. And our second formula, oh, I think I got a mistake here. We're going to compound continuously at 6.88%. Don't you like it when I make mistakes? So this is going to be, let's fix that mistake. So the 7% is for compounding daily, and the 6.88% is for compounding continuously. So that would be 0.0688. Let me make that substitution now. 0.0688 times 4. All right, and in the other calculation, we're going to have the 10,000 times 1 plus, I'm investing at 7%, compounding daily, so that's 365 times to the 365 times 4. All right, so I didn't leave myself a lot of room. Let's look at continuously. So when I did my formula for continuously, which I honestly can't spell, when I took my calculator out and took 10,000 times E to the 0.0688 times 4, I get 13,167.94. And when I did compounding daily, so I take 10,000 times 1 plus 0.07 divided by 365 raised to the 365 times 4, I got 13,230.94. So comparing the two, it looks to me like the 7% compounded daily is going to give me a better return. So I'll choose that one. All right. Problem 4, we have an exponential equation that we want to write in logarithmic form. So remember, our exponent is what our log is equal to. So our exponent here is A. can write that in the space. And that's going to be equal to the log and our base here. The base is the number 7. So it's log base 7. So you're going to use a subscript right next to that log to show that that's the log base 7. And it's the log base 7 of 133. So 7 to the a equals 133 is the same as log base 7 of 133 equals a. All right, problem 5. Begin by graphing f of x equals log x. Use transformations of this graph to graph the given function. Graph and give the equation of the asymptote. Use the graph to determine the function's domain and range. So now we're going to graph a logarithmic function. And a logarithmic function has this shape that looks like this. Let me draw it over here to the side. Something like that. But what are we doing to this logarithmic function? We're subtracting 3 from the function. So that is going to be a vertical shift down. We're going to take that entire logarithmic function and move it down 3 units. So this is a vertical shift. Minus 3. So you're going to go down 3 units. All right. So when you graph that, and it looks something like this. Like this. You can see it when you graph it exactly what it looks like. All right. So what's the vertical asymptote? Well, since you haven't moved this graph horizontally at all, you've only moved it vertically, the vertical asymptote doesn't change. The vertical asymptote of a logarithmic function is x equals 0. And since I haven't moved this to the left or right, I haven't moved the vertical asymptote. So it is x equals 0. And you do need to write it in the form of equation x equals. If you don't, it will be incorrect. What's the domain of this logarithmic function? Since I haven't moved it to the left or right, the domain of this function remains the same. The domain of the logarithmic function is the set of positive numbers, or from 0 to infinity. The range of a logarithmic function is the set of all real numbers. And just because we move this thing down 3 units doesn't mean that it changes the range. The range will remain the same. It will be the set of all real numbers. So the only reason you would change either the asymptote or the domain of a logarithmic function would be if you had shifted it to the left or to the right. So if you'd added something to the x or subtracted something from the x, so perhaps you had like the log parentheses of x plus 2 or the log parentheses of x minus 4. So when it's in parentheses and you're subtracting something or adding something to the x, that's when you change the domain of the logarithmic function. Moving it up or down, it's not going to change its domain. For example, problem 6. Find the domain of the function h of x equals the log base 6 of x plus 4. Now, can you see the difference between that and the previous problem? Now you have the log base 6 in parentheses of x plus 4. So what you're doing here is you're shifting the function to the left 4 units. Remember, when you add something to x, you shift to the left. If you subtract something from x, you shift it to the right. So when I move this entire function to the left, negative 4, to negative 4, I move the domain of this function also. So the graph would look something like this. The vertical asymptote would move to x equals negative 4. So when that happens, I move the whole domain 4 units to the left. So the domain is going to be from negative 4 to infinity. Now, the other way you could look at this certainly is to say, well, wait a minute, if I'm taking the log of x plus 4, x plus 4 must be a positive number. I cannot take the logarithm of anything except positive numbers. So x plus 4 has to be positive. So you could set x plus 4 greater than 0. That means it would be to the right of 0, which means it would be positive. Subtract 4 from both sides. X has to be greater than negative 4. And if it's greater than negative 4, that means it's all the numbers to the right of negative 4 or from negative 4 to infinity. Problem 7, write the equation in its equivalent exponential form and then solve for x. So this is our first solving of logarithmic equations. And to solve this logarithmic equation, you're going to write it as an exponential. So the first step is just to write it as an exponential. Don't solve it or anything like that. Just write the logarithmic equation as an exponential equation. So remember, what my logarithm is equal to is my exponent. So my exponent is going to be 3. But what am I raising to the third power? Well, my base is 2. So I'm raising 2 to the third power, and that's going to give me what I'm taking the log of. So the first part of this, I'm just going to write 2 to the third power equals x minus 2. That is the equivalent exponential equation. And now I solve this, and it's pretty simple to solve. 2 to the third power is 8. Add 2 to both sides, and we get what? X is 10. All right, use the properties of logarithms to expand the logarithmic expression as much as possible. Evaluate logarithmic expressions without using a calculator if possible. So I have the logarithm of a quotient, and I have a property that says that if I have the logarithm of a quotient, I can write that as the difference of those two logarithms. So I can write this as the natural log of e to the 5th minus the natural log of 15. But when I take the natural log of e to the 5th power, the natural log of e to the anything is just that exponent. So the natural log of e to the 5th is the number 5. And I'm going to leave the natural log of 15 as the natural log. So this is going to be 5 minus the natural log of 15. All right, so the next problem is to go the opposite direction, to take an expansion of logarithms and to condense it. Use the properties of logarithms to condense the logarithmic expression below. Write the expression as a single logarithm whose coefficient is 1. Where possible, evaluate logarithmic expressions. Okay, so I got two rules that I'm going to be using here. The first one is the power rule. So I have outside my first logarithm the number 5, so 5 is a factor. So I can take that 5 into the logarithm as an exponent. That's the power rule. So I can take the 5 in and make it an exponent on the x. I can do the same thing for the second logarithm. I have a factor of 4 outside that logarithm, so I can take that into the logarithm as an exponent. So I've used the power rule. So now I have the difference of two logarithms. If I have the difference of two logarithms, I can write that as the logarithm of a quotient of those two things. So I can write this as the natural log of x to the 5th over y to the 4th. All right, our next problem. Use common logarithms or natural logarithms in a calculator to evaluate the expression. So we're going to use the change of base property. And the change of base property says that if I have the log of any base except 10 or e, I can find that logarithm just using this change of base. What you do is you take the common log of the number and divide that by the common log of the base, or you can use the natural log. They give you exactly the same answer, exactly the same answer. So you can use either one of those, whichever one you want to use. Now, be sure that when you're doing this on your calculator that you close your parentheses. When you hit the logarithm key on your calculator, it will open parentheses for you. Just be sure you close those. If you don't, you're not going to get the correct answer. So when I did this, I got 0.094757, some more numbers out there to the right, but it tells me round to 4 decimal places as needed. So I want to round to 4 decimal places. So I look at my 5th decimal place, that's a 5. So I need to round the 1 up to 2. So approximately this value is 9472. All right, problem 11. Solve the following exponential equation by expressing each side as a power of the same base and then equating exponents. So this is the method we learned to solve exponential equations. It's called the matching base method, where you're going to match the base on each side of the equation on the left-hand side and the right-hand side. On the left-hand side of this equation, I have a base of 5. So I want to look at writing 1 over 125 with a base of 5. And I can do that. I can write 1 over 125 as 1 over 5 cubed. 5 times 5 times 5 is 125. And then I can use the laws of exponents. The laws of exponents says that if I have a number raised to a power in the denominator of a fraction, I can rewrite that in the numerator raised to the negative exponent. So this is 5 to the minus 3. 5 to the minus 3 and 1 over 5 to the third are the same thing. That minus sign in the exponent means to take the reciprocal of that value. So it means to take 1 over 5 to the third. All right, so now that I have the bases matched, I have 5 to the 4 minus x equals 5 to the minus 3. Once the bases are matched, I can set the exponents equal to each other. So 4 minus x equals negative 3, and then solve for x. Now the most common mistake I see when you're solving for x in this equation, and again, pretty transparent here, most of these that you solve, there's going to be a minus sign in front of the x when you solve it. And that's fine, just don't lose the minus sign. That's the error I see most often. Because if I subtract 4 from both sides, on the left-hand side of this equation, I have negative x. And on the right-hand side, I have negative 7. So to solve for x, I need to divide both sides by negative 1. So x equals 7 is my solution. So my solution is the number 7. All right, the next problem, solve an exponential. Solve the following exponential equation. Express the solution set in terms of natural logarithms or common logarithms. Then use a calculator to obtain a decimal approximation for the solution. So you're going to solve it first in terms of the logarithm, and then you're going to find a decimal approximation using your calculator. All right, to solve an exponential equation of this type, you must isolate the exponential. That means I need to get rid of the 5. I cannot solve this until I get the 5 out of there. So I'm going to divide both sides by 5. Let me write this over here. And when I divide 965 by 5, I'm going to get 193. And now I can take the natural log of both sides of this equation. And I am going to take the natural log because the base is e, so it makes sense to take the natural log. And when I take the natural log of e to the any power, that's going to be equal to just the power itself. So this is 7x equals the natural log of 193. Divide both sides by 7, and I get x is the natural log of 193 divided by 7. And that is the first answer I'm going to input here. So I have the natural log of 193, the whole thing divided by 7. So that's the first answer I input. The second answer I'm going to input is the decimal approximation to this. So I'm going to take my calculator out and find the natural log of 193, get that value and divide it by 7. And when I do that, let me see what I got here. I got 0.7518, and it tells me to round to 2 decimal places. So I'm going to look 1 decimal place to the right of the 5, that's a 1. So I don't round up, I'm just going to write that as 0.75. All right, problem 13 is solving a logarithmic equation, but in this case I have 2 logarithms, and to be able to solve a logarithmic equation I have to have it written in terms of a single log on one side of the equation and a constant on the other. And the reason I have to do that is because the way I'm going to solve this logarithmic equation is to write it as an exponential. And the only way I can write it as an exponential is to have a single logarithm. So since I have the sum of 2 logs here, I have a property for the sum of 2 logs, and I can write the sum of 2 logs as the log of the product. So it's the product rule. So I can write this as the log base 4 of x times 3x minus 1 equals 1. So the sum of 2 logs I can write as the log of the product of those 2 things. Now I'm going to write this as an exponential, and this is where I see the mistake most commonly made, except for the mistake of not checking your answers, is not getting that base raised to the exponent. The base in this logarithm is the number 4. And I'm raising it to the first power. Remember, what your logarithm is equal to is the exponent that you're raising that base to. So I'm raising 4 to the first power, and that's going to be equal to x times 3x minus 1. And so now I have a quadratic equation, and I can solve a quadratic equation by either using factoring or using the quadratic formula. But I first must get it in standard form. So I need to get everything on the left-hand side of the equation and 0 on the other. So I've got a little multiplication and addition and subtraction to do here. So I'm first going to distribute the x across the 3x minus 1. And that's 3x squared minus x. And then I'm going to subtract the 4 from both sides. And I get 3x squared minus x minus 4 equals 0. And that is factorable, and I'm all about factoring if I can. Quadratic formula just takes too long. I think that's going to be a 4 there, 1 there, and that's going to be minus, and that's going to be plus. So then we're going to set our 2 factors equal to 0. So we get 3x minus 4 is 0, or x plus 1 is 0. Add 4 and divide by 3. So I get 4/3 or -1. So now I got to pause before I type both of these numbers in to the solution box in my MATLAB and hit submit. I'm going to do a quick check to make sure that neither one of these numbers, or both of them maybe, violate the domain of the logarithm. Okay, let's first look at 4/3. Can I take the log base 4 of 4/3? Yes. And I can take the log of 4/3 because it's a positive number. So it doesn't violate the domain in the first logarithm. Now let's put it in the second logarithm. Can I take the logarithm of 3 times 4/3 minus 1? And the answer is yes, because that's going to end up to be 3 times 4/3 is 4, 4 minus 1 is 3. So yes, I can take the logarithm of it. So 4/3 is the solution. How about the -1? Oops, doesn't work. Immediately, doesn't work. Because if I put -1 into that first logarithm, the log base 4 of -1 does not exist. So -1 is not a solution to this equation. It's extraneous. So the only solution to this equation is 4/3. Remember, when you solve a logarithmic equation, you must check your solution to make sure that it doesn't violate the domain of the logarithm. If it violates the domain, which is the domain of the logarithm, it's a set of positive numbers, you cannot take the logarithm of 0. You cannot take the logarithm of a negative number. So if it violates your domain, it is not a solution. All right, problem 14. The formula A equals P times e to the RT describes the accumulated value A of a sum of money P, the principal, after T years at annual percentage rate R in decimal form, compounded continuously. Complete the table for a savings account subject to continuous compounding. So the amount that you're investing is $7,500 at an annual interest rate of 8%, which we do need to write as a decimal, so we divide it by 100. And we're doubling the investment. So how long is that going to take? So the amount that you accumulate then, since you're doubling, is going to be $15,000. If I double the amount in my investment after T years, then I'm going to have $15,000 when I'm done. All right, so now we're just going to plug everything into this formula and solve for T. So what do I have? 15,000 equals 7,500 e to the 0.08t. All right, this is an exponential equation, so I need to isolate the exponent to be able to solve it. So I need to get rid of the 7,500. I'm going to do that by dividing both sides by 7,500. So I get 2 equals e to the 0.08t. Now I'm going to take the natural log of both sides. So I have the natural log of 2 equals, when I take the natural log of e raised to a power, that's equal to that power. So this is 0.08t. So to solve for t, I divide by 0.08. So I take my calculator out, make sure I close my parentheses on my logarithm, take the natural log of 2, whatever that is, and divide that value by 0.08, and I get t is approximately 8.66. And they tell me to round to 1 decimal place, so I would round the 6 up to 7, because I look at the decimal to the right of the one I'm rounding off. If that's 5 or greater, I round up. So I'd round this up to 8.7. All right, 2 more problems. Problem 15 is ridiculously easy. Sorry. So you should all get that one right. The exponential model A equals 926.1 e to the 0.03t describes the population A of a country in millions P years after 2003. Use the model to determine the population of the country in 2003. So that's t equals 0. If t is the number of years since 2003 and you're in 2003, t is 0. So plug that in. Well, 0.03 times 0 is 0. e to the 0 power, any number except 0 raised to the 0 power is 1. So e to the 0 is 1. So what's the population? 926.1. Boy, you all better get that right. All right, last but not least. An artifact originally had 16 grams of carbon-14 present. The decay model is, they give me the decay model. Well, that was awfully nice of them. A equals 16 times e to the minus 0.000121 t describes the amount of carbon-14 present after t years. Use the model to determine how many grams of carbon-14 will be present in 9,603 years. So it's a plug and chug because they give you t. So you're going to take your calculator out and you're going to multiply 16 times e to the 0.000121 times 9,603. And when I did that, I got 5 when I rounded that off to the nearest whole number. And that is the end of the review. There are 16 questions on your review. As you all know, the review and the test are almost identical. So 16 problems just like these. Thank you.